Welcome to part 2 of my lecture series on Large Eddy Simulation, or LES. In part 1 of this series, we looked at some introductory concepts for LES, such as the Turbulent Kinetic Energy cascade, the integral length scale, and how we might put together an initial mesh for LES calculations. In this talk, in part 2, we're going to be looking at what happens after you've carried out your first LES calculation. What sort of quantities should you be looking at? What do they mean? And how can you assess whether that initial mesh that you generated was good enough for practical LES? So if you're a new user of LES, or if you're thinking about moving from RANS calculations to LES calculations, I know this talk is going to be perfect for you. So sit back and take some notes. I know you're going to find this talk extremely useful. So just to start with a quick background for this talk, we're looking at Large Eddy Simulation. And in a Large Eddy Simulation, what we have in our CFD domain is we've got a number of eddies which are resolved by the mesh, which you can see there in the diagram. And we've got large eddies and we've got smaller eddies there. And what we find is that if we put a point probe or a point monitor in the mesh when we run our CFD solution, we'll find that the point probe will see contributions from all of those eddies that are being resolved by the CFD mesh. And that will result in a kind of a turbulent, erratic fluctuation in the signal, which you can see there in blue in the image. And of course, all of these eddies are superimposed on top of each other, so you won't necessarily be able to see all of them, but numerically, all of these eddies are superimposed on top of each other, and they'll all be captured in the point probe signal. Now, if we put point probes at different locations in the mesh, so if you set up your CFD calculation and you put a range of different point probes all around the CFD domain, what you'll find is that, of course, each of those point probes will see a different signal in the velocity, the temperature, and the pressure with time. And of course, that's because there are different eddies at different locations in the flow field. And more importantly, the mesh will be resolving a different degree of those eddies at the different locations in the domain. So we've got different point probes in different locations, and they're all going to be resolving different fractions of the energy spectrum. And what we'd like to know is our CFD calculation sufficiently resolved for the LES? And more importantly, where in the domain is it sufficiently resolved and where is it not sufficiently resolved? Because we're quite likely to have a situation where the mesh that we've constructed for the LES is good enough in some areas, but isn't good enough in other areas. And what we'd like to do is find where those areas are, so then we can go back to the mesh and refine it so that our later LES calculations will be able to resolve more of the flow field. And what's the method of approach? Well, in this talk, I'm going to be proposing a very simple method for assessing the mesh and how good it is. And the basis of this method is to use the turbulent kinetic energy to assess if the mesh is sufficient. And I should emphasize at this point that we're only making an assessment, a preliminary assessment of the mesh only at this stage. There are other things which you'll want to look at for your LES calculations, such as the time stepping and the total length of your simulation, but we're not going to be looking at those things in this talk. I'm just going to be looking at if the mesh that we made in the previous talk, if that mesh is good enough for the LES, and where is it good enough and where is it insufficient. And the criteria that we're going to be using in this talk, which tends to be a good enough criteria for most LES simulations, is that good LES will resolve at least 80% of the total turbulent kinetic energy. And what does that statement mean? Well, if we think back to the turbulent kinetic energy density graph that we came up with in the previous talk, what this means is that the total area under the graph is the total turbulent kinetic energy, and we want to ensure that our LES resolves at least 80% of that. And that's generally the criteria for a good LES simulation in terms of the mesh. And so what we want to do is we're going to propose a method for looking at the mesh and see, does it resolve at least 80% of the turbulent kinetic energy? If it doesn't, then we're going to have to go back to the mesh and refine it. So this process has got a number of different stages to it, and the way I'm going to go through these stages is by explaining them with diagrams so that you really understand what's going on. And in some cases with your CFD code and your CFD results, you'll be able to skip many of these stages and you'll be able to perform the analysis just with a few lines of code or post-processing. But I think that it's important that we understand exactly what we're doing so that we can make sure that we get the right answer when we're doing the post-processing. So if we think back to those point probes that we looked at earlier, each of those point probes is going to show that sort of turbulent, erratic signal at different locations in the domain. And the first thing that we want to do is to carry out a time average of that signal. So just as a reminder, when you're solving the LES equations with conventional CFD code, the CFD code is going to be computing the instantaneous velocity field. So you can think of that as the erratic signal, the local or the instantaneous velocity that contains the mean and the turbulence. That's what the CFD code is solving for. And so when you put point probes in the domain, what you're actually looking at is the evolution of the instantaneous velocity at that location in the domain with time. And the first stage in our process for assessing the mesh is we're going to do a time average of that signal to calculate the mean velocity, which I'm going to call U bar here, although some references will use triangular brackets instead of an overbar. And of course, when we do the time averaging, what you want to do is make sure that the simulation is sufficiently converged for you to carry out your time averaging. And some places will call this a statistically steady state. That's what you want to be looking for with your CFD calculation. And I'm going to go into more detail into the time averaging process in another video. But for now, what you want to do is just make sure that your LES simulation has run a sufficient length of time and then carry out a time average. And that's going to give you the mean velocity field, which we're going to call U bar. And of course, the way to do this is not to average the point probes themselves. What you want to do is to average the entire flow field. And most CFD codes will be able to do this for you with the statistics averaging packages that they contain. And so how this will look is the CFD code is going to compute that instantaneous velocity field, which you can see in the top figure. And then through the statistics averaging in the CFD code, we're going to calculate the mean velocity field, which is U bar. And just from looking at those images you can see on the slides, the instantaneous velocity field, of course, you can sometimes see the eddies and you can see the unsteadiness in the flow field, but the mean flow field is probably the one that you're more used to looking at and analyzing in your post-processing. So this is the first stage in the analysis, is just calculating that mean velocity field. And most of the time CFD code's able to do this for you. So you won't need to do any complicated post-processing like deriving new fields and things. Just enable the statistics averaging in your CFD code. But for now, of course, we're going to have to do a bit more effort if we want to calculate the turbulent kinetic energy. So if we just think back to that point probe measurement that we have for the velocity field, this will help us to understand the fluctuating velocity. So if you look at the figure on the left, that's the fluctuating velocity at a zoomed in location in the point probe. And what we do is we get the CFD code to calculate the mean velocity, which is given by that dashed line you can see in red there. That's the mean or the average. And then the conceptual stage that we're going to do is to subtract the mean from the instantaneous velocity field. And that will give us the fluctuating velocity, which I've denoted by U with a prime there. And you can see that in the image on the right, which is in blue. And U prime is just the fluctuations associated with the turbulence. So of course, if you were running a RANS calculation, you wouldn't have any of these fluctuations because you'd only be looking at the mean, which is U bar. And the reason we want to isolate the fluctuations, U prime, is we're going to use these to calculate the turbulent kinetic energy. So conceptually, what we've done so far is we've started with the instantaneous velocity field U. That's the velocity field that the CFD code computes when it solves the equations. And then we get the CFD code to carry out the time averaging for us in the statistics packages that the CFD code will have. That gives us the mean velocity field. And then we subtract the mean velocity field from the instantaneous, and that allows us to isolate the fluctuating velocity. So the figures that I've got for you on the slide here really emphasize that these are three different velocity fields. So at every cell in your mesh in the CFD calculation, you've got a value of u, you've got a value of u bar, and you've got a value of u prime. These are different things, and we can extract all of them from the LES results. And now what we want to do is to calculate the turbulent kinetic energy in the fluctuations. And when we think of the turbulent kinetic energy, we want to think about this as the energy associated with that fluctuating velocity field u prime. And when we calculate this turbulent kinetic energy, this is going to be the turbulent kinetic energy resolved by the mesh. And the reason it's resolved by the mesh is that at each of those cells in the domain, we've calculated a fluctuating velocity u prime. And so that means that it's physically resolved by the mesh. Whereas, of course, in a RANS calculation, we haven't actually calculated a value of u prime there. We've modeled it, so the turbulent kinetic energy would not be resolved in the RANS calculation. And how are we going to calculate this kinetic energy in the fluctuations? Well, if we just think back to the definition of kinetic energy is normally half m times velocity squared, where the m is for mass, but we want the kinetic energy per unit mass. So we're going to have to multiply this fluctuating velocity components together to get the u squared, and that's going to allow us to put together a calculation for the kinetic energy. Now, if we think of the fluctuating velocity, of course the fluctuating velocity has three different components, because we have a velocity field in three directions, x, y, and z, and there's going to be a different mean in each of those directions. The mean could be 0, but there will still be a velocity component in each direction. And what that means is that if we subtract the mean in each direction from the instantaneous velocity in that direction, we have three different components of the fluctuating velocity. And so if we want to get the turbulent kinetic energy, we're going to have to multiply these velocity components together. And because we have three different fluctuating components, there are going to be 9 different possible combinations of those velocities multiplied together. And these combinations are often referred to as the instantaneous Reynolds stresses, because they're going to be the stresses associated with the fluctuating velocity. And these are instantaneous at the moment because we've just taken the velocity field and multiplied them together. Now, to calculate the turbulent kinetic energy, we only care about the normal components. So that's u multiplied by u, v multiplied by v, and w multiplied by w. We want the normal components of the Reynolds stress. At the moment, we're not concerned with those cross terms, the uv and the wv terms. We only care about the normal components for the turbulent kinetic energy. But for now, what we need to do is we need to average the product of those components, and we've denoted that by an overline or an overbar, which you can see there in equation 6. So we've got all the velocity components multiplied together, and then we've taken a time average over the top, and that will give us the Reynolds stress that we're used to from our RANS calculations. Now, there's a small side point which I wanted to make here, which should help clear up any confusing points that you might have at the moment. If you think of the fluctuating velocity component, which I've got for you there on the slide, that's the u prime. If you take the time average of this, the time average is going to be equal to 0. And the reason the time average is equal to 0, of course, is we subtracted the mean before. So that means that the average of this component, because we've moved it down, that's a way of thinking about it on the axis, is the average is going to be 0. Or graphically, the area under the curve is going to be equal to the area above the x-axis there. So they average out, and the average of the fluctuating velocity is equal to 0. So what this means in practice is that when we calculate the Reynolds stresses, we need to multiply the velocity components together first and then take the time average. Because if you took the time average first, the time average would be 0, and then 0 multiplied by 0, of course, is still 0. So just a small point on notation there. This is why you often see the averaging bar or the triangular braces are above those stress components, because we have to take the average after multiplying the velocity components together. And in terms of the kinetic energy, of course, if you multiply u by u, the square is always positive. So if you had u squared and then averaged, that value is going to be non-zero, which is part of the reason why we take the average after multiplying together. So what we can do is we can collect those 9 components of the resolved Reynolds stress tensor together in a matrix, and this is commonly shown, as you can see, in equation 8. And just a note, of course, that this, strictly speaking, is the Reynolds stress tensor per unit density. We've taken the density out of this. I just want to focus on the Reynolds stress tensor per unit density in this talk. And another useful point to note as well is that, of course, when you multiply the velocity components together, if you multiply u by v or u by w, the order of multiplication doesn't matter. So u multiplied by w averaged is the same as v multiplied by u and then averaged. And the reason that's an interesting point and useful to remember, of course, is it means that there are actually only 6 independent components of the Reynolds stress tensor. And so I've simplified that for you in equation 10, which you can see there, that of course uv will be equal to vu, wu will be equal to uw, and vw will be equal to wv. So really the Reynolds stress tensor is sometimes called a symmetric tensor, and it only has 6 components. It's got the 3 components along the diagonal. These are the normal components that we're interested in for the turbulent kinetic energy, and then there are the cross terms, which are the off-diagonal components of the Reynolds stress tensor. And just to emphasize what we've spoken about before, once we have this resolved Reynolds stress tensor, we're going to take those diagonal components and add them together, and that will give us the resolved turbulent kinetic energy. And the reason that we add the diagonal components together is we may have, if we think of a flow field, we may have some turbulent kinetic energy in the x direction, some in the y direction, and some in the z direction, but we're concerned with the turbulent kinetic energy at the point, which is a scalar value, and so we want the sum of that energy in each of the different directions added together. And that's why you'll see the turbulent kinetic energy as the sum of UU, VV, and WW. And another point which I wanted to make here, which hopefully will clear up any confusion for you if you go looking for this in the literature, is that some sources will write U prime squared instead of U prime U prime. It means the same thing. They're just using different notation to denote U multiplied by U, V multiplied by V, and W multiplied by W. So now that we've done that little bit of background, you should hopefully have a better understanding for some of the quantities that the CFD code will kick out for you in the post-processor. So if you're an OpenFOAM user, for example, you'll see the matrix U prime to mean, which is given out by the CFD code. And based on the analysis that we've just been through, you'll see, of course, that this is the matrix of the Reynolds stress tensor per unit density. And of course, it's got 6 components. It's a symmetric tensor, which is why if you open up that file in OpenFOAM, you'll see that there are actually 6 entries rather than 9. And that's because it's symmetric, as we went through before. And you'll also notice that this field has the units of meters squared per second squared, which of course is consistent with velocity squared. So if you open up that U prime to mean file, you should now have a good understanding for what OpenFOAM's actually calculated and produced for you. Meanwhile, if you're an ANSYS user, you'll see that ANSYS gives you access to quantities such as velocity RMSE, or root mean squared error. And that term has units of meters per second. And in order to understand that term, you can see that if you take the square root of U prime squared, that of course is going to have units of velocity, or meters per second. And so what ANSYS is doing for you is it's giving you the square root of each of those terms on the diagonal, which has units of meters per second. And why is this important? Well, there's a slight difference for how you're going to calculate that turbulent kinetic energy if you're an OpenFOAM user or an ANSYS user or another CFD code. You can see that for the ANSYS users, you're actually going to need to square that root mean squared velocity in order to get the U prime, U prime, V prime, V prime, and W prime, W prime. Whereas if you're an OpenFOAM user, you can just take the diagonal components of that matrix directly. So really the important point of this slide is to be careful and check what quantity the CFD code is giving you. And a quick check of this is always to just look at the units, and that will very quickly tell you whether you're looking at the square root or the actual term itself. So now that we've been through the theory, what you can do is you can open up your post processor and very quickly calculate a new field, which is the resolved turbulent kinetic energy. And as a new field, you can of course plot it as a contour plot. And of course, depending on your post processor will depend on how you calculate this field. So if you're an OpenFOAM user and you're using ParaView, you'll of course need to open up the calculator tool, and the equation there given on the slide for you will show you how to calculate that resolved turbulent kinetic energy. Whereas of course, if you're an ANSYS user and you're using CFD post, CFX post, or another post processor, be careful that you need to square those RMSE velocity terms so that you can get the right turbulent kinetic energy. And just looking at the resolved turbulent kinetic energy field, you can see some of these similarities that intuitively you'd expect if you carried out a RANS calculation. You can see that there are going to be high areas of turbulent kinetic energy, for this case at least, in the shear layer that's shed off the backwards facing step. And if you're carrying out another CFD case, you'll probably be able to identify areas of high turbulent kinetic energy are where you would expect them to be from a RANS calculation. So now it's worth making a very important point that what we've just calculated in the post processor is the turbulent kinetic energy that's resolved by the mesh. And I've used the subscript notation K sub res there to be absolutely clear that this is not the total turbulent kinetic energy. And in a RANS calculation, as a reminder, what we're solving for is the total turbulent kinetic energy, which I've used just the plain notation of K there. And if we think back to our plot of the turbulent kinetic energy spectrum, just a reminder that the total area under that curve is the total turbulent kinetic energy, K, which is what we calculate in the RANS calculation. But what we've just calculated in the post processor is the resolved turbulent kinetic energy. So that's the area under the curve to the left of that dashed line, which you can see there. So we've calculated a big chunk of the turbulent kinetic energy, and we'd like to use this to assess, are we resolving at least 80% of the total turbulent kinetic energy? But in order to make that calculation and to work out, do we have at least 80%, we need to work out what that remaining area is. We need to work out what the subgrid scale turbulent kinetic energy is. And that's what I'm going to show you in the rest of the talk. And then to wrap up, once we've calculated both of them, we'll be able to evaluate how much of the total turbulent kinetic energy our mesh is resolving, and therefore how good our LES calculation is. So before we get started, it's useful just to think about what is the subgrid scale turbulent kinetic energy? What does it physically mean when we're trying to calculate it? Well, if we think back to our mesh, we are reminded that the mesh is not able to resolve all of the eddies. And the eddies that are smaller than 4 cells, which you can see there in the diagram, those eddies are going to be contained within a CFD cell. And the CFD code is not able to resolve those eddies because you need at least 4 nodes to get the resolution of an eddy or a circular motion. And those eddies that are contained within a CFD cell that we're not resolving, they also have kinetic energy associated with them. And the subgrid scale kinetic energy is the kinetic energy of those eddies that are contained within a CFD cell that we're not resolving explicitly. And now it's worth pointing out that if you're an OpenFOAM user, you're very lucky, because the OpenFOAM code calculates the subgrid scale kinetic energy for you and writes this out as a field, and that's the field K. So if you're an OpenFOAM user, when you look in your time directories, you'll see a number of different fields and a turbulent kinetic energy field K. This is the subgrid scale turbulent kinetic energy field. So you would then need to calculate the resolved turbulent kinetic energy as we showed previously, and then you've got both components and you can just skip the stages here. But if you're an ANSYS user or some other CFD codes, you need to put in a bit more work in order to calculate the subgrid scale turbulent kinetic energy, and you can do that in your post-processor. So the reason that it's difficult to determine the subgrid scale turbulent kinetic energy is that the method that you use depends on the subgrid scale model that you've selected. So if you've got the Smagorinsky model or a dynamic turbulent kinetic energy model or something different, the method that you chose for your subgrid scale model when you selected it is going to give you, you're going to need a different method to extract the subgrid scale turbulent kinetic energy, and that's why it's difficult. So the easiest models are the models that use a kinetic energy transport model, and if this is the model you selected, then it's fairly straightforward, because the CFD code will solve a transport equation for the subgrid scale turbulent kinetic energy, much like you would for the other equations, and then this field, K with the subscript SGS, is already exported for you and is available as a solution in the post-processor. So you just need to make sure that you read in that field and you can look at it directly in the post-processor. That one's fairly easy. But what if you were using a different subgrid scale model to calculate the dynamic viscosity? Well, for some of these models, you can calculate the subgrid scale turbulent kinetic energy from the subgrid length scale. So if you go looking into the literature and trying to find out how to calculate the subgrid scale turbulent kinetic energy, a lot of sources will tell you that you need to calculate it from the subgrid scale length scale. But what does this physically mean? We can use equation 18 to get K directly from the subgrid length scale, L SGS, but what actually is the subgrid length scale and what does it physically mean? Well, if we think back to the previous talk where we looked at the integral length scale, that's a length scale that categorizes all of the eddies at a different location in a CFD domain, that can help us to understand what a subgrid length scale is. So what I want you to do is think about one of the cells in a CFD mesh, and I've got those for you in a figure on the slide, which you can see there. And within that cell, of course, you're going to have eddies of a variety of different sizes. You're going to have some large eddies and some small eddies. And what we could do is we could define the size of an eddy that's representative of all of the eddies within that cell. And the size of that eddy is representative of the size of an eddy that has the same turbulent kinetic energy as the average of all of the eddies within that cell. So if you look at the eddy which I've shown for you there in red, it's about a medium-sized eddy. That's what you would physically expect. And that's because, of course, the eddies that are larger than this will have more kinetic energy and the smaller ones will have less kinetic energy. And so the length scale, the subgrid length scale, is just the size of that eddy that has the same turbulent kinetic energy as the average of all of those eddies that are stuck within a cell that we haven't managed to resolve. And this is really the same idea as an integral length scale, but now we're just zooming in on a single cell in the CFD mesh. And so if we think back to that diagram, how large do we expect that representative eddy to be? Well, physically, the eddy can't be larger than the cell. That eddy has to be contained within the cell. And so what we could do is we could specify the length of that eddy as a fraction of the cell size. And in practice, that's what people do. The subgrid length scale is defined as some constant multiplied by the cube root of the cell volume. And the cube root of the cell volume just gives you the approximate size of the cell. So our eddy is going to be some fraction of the cell size, and in practice, most people use the Smagorinsky coefficient for this, which turns out at about 0.1, or depending on the source, you may have different values for that. So what you would do is you look at your CFD code and look at the value of the Smagorinsky coefficient that your CFD code is using, and you use this to define what the subgrid length scale will be in that cell in the CFD domain. And of course, this is a field that you can define for all of the cells in your mesh. So for all of the cells in your mesh, in your post-processor, you take the cube root of the cell volume and then multiply it by the local Smagorinsky coefficient, depending on the model that you're using in the CFD code. And that will give you the subgrid length scale. And then you can go back to that previous equation, and that will give you the subgrid scale turbulent kinetic energy. So after a few stages, you can manage to piece together that subgrid scale turbulent kinetic energy. And there is one small modification that I just wanted to draw your attention to, because if you look at some of the CFD manuals and at some of the references, you'll see that the formula for the subgrid length scale is modified slightly. And the reason it's modified is if we think of what physically happens to the eddies as we get closer to the wall, then the size and the energy of the eddies is going to be damped by the presence of the wall. And really, the way you can think about it is that if you move away from the wall, then the eddies that are contained within that thin sublayer are going to be smaller than the cell size. And so what you'll find is you'll often find a modified formula for the subgrid length scale, which I've got for you there in equation 20. And the subgrid length scale, or the effective size of that eddy close to the wall, is going to be the minimum, or whichever is smaller, of the distance from the wall and the cell volume itself. And this is very useful in practice because it gives us a better calculation and estimation for what the subgrid scale turbulent kinetic energy is in those cells that are very close to the wall. And another way you can think about this, of course, is that when the cells have very high aspect ratio, the eddies that are going to be contained within that cell are going to be slightly different if you have a more cube-shaped cell. And that's why this modification is present. So now to wrap all this up and bring it back to where we were before, what we've done is in the post-processor for our CFD calculations, we've managed to calculate two new fields. The first one that we've calculated is the resolved turbulent kinetic energy, which I've called K-res for you there. And the other field that we've calculated, either directly ourselves or the CFD code has given it to us, is the subgrid scale turbulent kinetic energy. And what you can see from the pictures, of course, is that these two fields are different. They have different values and they look very different, but the range and the scales are very similar. And the key aspect of this analysis, which is what we're going to use to assess the quality of our mesh, is to calculate the ratio of these fields. And we're calculating the ratio of the resolved turbulent kinetic energy to the total turbulent kinetic energy. So that's K-res plus K-SGS. And really, this is an important point, and the reason I've got for you a contour plot on the slide is that this is a field that you've calculated for the entire CFD domain. So K-res, K-SGS, and the ratio are all fields that you can calculate in the post-processor, so you can look at them. And what this ratio is telling you is it tells you the fraction of the turbulent kinetic energy that the LES mesh is resolving. And as a reminder, you want to aim for at least 0.8 or 80%. And for the example that you can see here on the slide, you can see that all of the color contours are in the red and orange range, and this is telling us that the mesh that we currently have in most of the domain, except for some of those regions close to the wall, if you really zoom in, is greater than 90%. And so what that's telling us is that the mesh we have based on this metric is good enough for LES, and that the free stream mesh will resolve at least 90% of the turbulent kinetic energy. And this is fantastic for our LES. In this case, of course, there are some small regions closer to the wall where we're not quite achieving 80%, and so we may have to go back and remesh those regions close to the wall. It really does vary throughout the CFD domain, so you're going to have to look at your own calculation and try and look at what areas are good enough and what areas are already sufficient. So now I'd also like to bring this back to the turbulent kinetic energy density diagram to help with your understanding. So if at this point the contours identified that some of the mesh was not sufficiently resolved for LES, what we would have to do is go back to the mesh generator and refine the mesh locally in those positions. And what happens physically when we do this, of course, is that the turbulent kinetic energy density graph changes from the one you can see on the left to the one you can see on the right. The ratio of the resolved turbulent kinetic energy and subgrid kinetic energy changes, and as you make the mesh finer and finer, the area under the curve of that subgrid scale kinetic energy reduces as we resolve more and more of the turbulent kinetic energy. And what we're trying to do with the mesh is to get as much of the mesh as we possibly can to greater than 80% of that total area. So just to summarize the points that we talked about here today, the metric that we've been using to assess the mesh for our LES calculations is that a good LES mesh will resolve at least 80% of the turbulent kinetic energy through the majority of the domain. And the way we can assess this statement and whether it's been satisfied is we can look at the percentage of the turbulent kinetic energy that's been resolved by calculating KRES and KSGS in the post-processor. And the advantage of doing this in the post-processor is that we calculate them as fields, and so we can plot them and look at the variation throughout our entire domain. And of course, of these two quantities, the resolved turbulent kinetic energy is reasonably easy and straightforward to calculate, but the subgrid scale turbulent kinetic energy is more difficult to calculate because it depends on the subgrid scale model that you've been using. So we've been through quite a few points in this talk, but the final point to emphasize is that there are more talks on LES to come, because of course there are many different facets of this analysis procedure that still require a lot more detail for us to go through. So that brings me to the end of the video. If you enjoyed the talk, leave a comment in the comments section. I really do enjoy reading and responding to your comments. They really do help me to get through the videos and to plan future videos. I've had quite a few requests to carry on with this LES series of lectures. Many people have said that they found it really useful. So let me know, are you finding this series of lectures useful? Do you enjoy them? Would you like to see more videos on LES? If you do, then of course I can start working on more videos for LES. And if you have other topics, for example, that you think would be more useful or a better use of my time, then again, just let me know in the comments section. I really enjoy hearing comments from you guys, and it really helps me to plan future videos so that I can make sure that they're the most useful for everyone. So until next time, thank you all for listening.